Hey everyone, how's it going? So in order for us to talk about kinetics revolving around reactions with enzymes and biological reactions, we first have to go to the fundamentals of chemical kinetics and talk about the things that affect rate, concentrations, and product formation. So let's talk a little bit about the fundamentals of what we are thinking about when we talk about chemical kinetics. So for example, we're looking at this rough example of reactant A turning into product B. And as we can guess, as time goes on throughout the chemical reaction, we're going to be decreasing in the amount of A in the container and increasing the concentration of B, till it's all B and none of A. The way that we're able to measure rate when thinking about chemical reactions is seeing how the concentration of a certain reactant or product changes over time. So that's moles over liters per second. But when we think about reactants, we know that they're going to be disappearing, so that's going to be the negative rate, the rate of disappearance. And when we have products like B, we know they're going to be appearing, so this is going to be the rate of appearance. But in real chemical reactions, we don't just have one reactant and one product. Sometimes we have a different ratio of reactants and products. And so when we have that, we're going to have varying rates. Things might disappear faster or slower. One thing to pay attention to is that if we have any coefficients in front of our reactants or our products, we have to make sure to divide the concentration by that number. So in this case, we can see that reactant A has a coefficient of 2, so its rate of disappearance is going to be divided by 2. About 4 basic points about things that increase the overall rate of a reaction. We have increasing temperatures that will increase the rate because we're increasing the thermal energy of our reactants moving. We have the increase of concentration since there's more reactants to react to form products. We have increase of surface area because if we increase the surface area, we're going to be increasing the area in which the reactants can react to form products, and the action of a catalyst, a lot like enzymes that we're trying to work to talk about later. Now that we're done introducing chemical kinetics and the fundamentals of rate, do you remember that animation that I had in the beginning of the video about how all these little reactants bouncing around and reacting around a membrane? This is going to help us understand our next topic about chemical kinetics, talking about ineffective reactions and effective reactions. This is all about collision model and energetics. But what is the concept behind an ineffective collision? So molecules are constantly bouncing off each other, hitting the walls of the container because they're constantly moving. But that doesn't mean they're always reacting because there's an energy barrier. This is what's called the activation energy. And if the activation energy is not achieved through a collision of the two molecules, we're not going to have a formation of products. So it's only when we have enough energy through the kinetic collision of the two reactants are we going to get a product formation. The second important factor to determine whether or not two reactants are going to react with one another is orientation. They can have the right energy all day, but if they don't hit each other in the right positions, there's not going to be a chemical reaction. So there's usually like a specific way or orientation the two molecules need to react with one another. So you can see here in this example that when the first one hits the blue side, nothing happens. But when the second one hits the yellow side, we have a chemical reaction happen. This is just a basic example of how orientation impacts chemical reactions. Okay, so we have the first two barriers when talking about chemical kinetics. We need the right collisions, but we also need the right energetics. But let's quickly go back to talking about activation energy for a little bit, because that opens the door for us talking about reaction energetics. If you've taken any science class, you've been introduced to the idea of exothermic and endothermic reactions. When you're first introduced to these types of reactions, you're probably introduced to them as reactions that absorb heat or release heat. So you would feel the container getting hotter or the container getting colder as a reaction occurs. But let's break down what's happening a little bit more than that. When we had the discussion of exothermic and endothermic reactions, we're talking about the potential energy difference between the reactants and the products. When the products have lower overall energy than the reactants, this is what we call an exothermic reaction, because throughout the reaction with the formation of the products, we're releasing that extra energy as heat. But with endothermic reactions, it's the opposite. The products have more energy than the reactants. So through the reaction, we're absorbing heat and energy from the surroundings. So with an endothermic reaction, you might feel the container getting cooler. But with an exothermic reaction, you're going to feel the container getting hotter throughout the chemical reaction. So we've established the basics about chemical rate, energetics, exothermic and endothermic reaction. We're beginning to put the foundations for us to talk about enzyme reactions and enzyme kinetics in the future. But one really important thing we have to talk about before, and this is going to influence things like equilibrium in the future, is the rate law. Opening the door to the rate law, we're opening ourselves to the ideas of some of the basic relationships when talking about chemical kinetics. This relationship focuses around concentration and rate. So here we can see the rate equation, right? R equals K, which is a reaction constant, the concentration of reactant A raised to M, reactant B raised to N. Now M and N are reaction orders. These can only be found experimentally. And so what the orders are going to be telling us is how that certain reactant impacts the overall rate of the reaction. Before we talk about the three most common rate orders, I just want to drive the idea of rate one more time to help us understand the impact of rate orders. Remember, the unit of rate is molarity per second. So no matter the different rate order we have, in the example, we have to make sure that the overall rate, the unit of it, is molarities per second. So our first example of rate order is first order. This is when M or N equals 1. So we can see in that case, K times the concentration of A raised to 1, but we don't really have to write it. Now, first order is all about that relationship between concentration and reaction rate is 1 to 1. So if we double the concentration, we're going to be doubling the rate as well. Now let's look at units. So we know that rate needs to be molarity over seconds. And we know that the concentration of A, that unit is molarity. So what does the concentration of the rate constant need to be? In the case for first order, it needs to be 1 over seconds. So that rate equals molarity over seconds. Now that we're talking about second order now, things change a little bit. Because now when the concentration changes, it has a greater impact on the reaction rate. So in this example, if the concentration in a second order reaction doubles, their overall rate will quadruple. That's a big effect. But now the units change. So look at our equation. We have R equals K, concentration of A squared, since we have a reaction order of 2. But now we have molarity squared. So the reaction constant, what did the units need to be? It's slightly cut off in the video, but the units of K need to be 1 over molarity times seconds, so that one of the molarities will cancel, and we'll be left with molarities over seconds for the rate of the reaction. And finally, the third most common rate order is zeroth order. This one's probably the easiest, because no matter how much we change the concentration, the overall rate of the reaction is going to stay the same. It's going to be 0. Now, the units of K are molarities over seconds, since we're not getting any units from the concentration, so that the reaction rate equals the reaction constant. And with that, we did a really good job at talking about rate, introducing the energetics of exothermic and endothermic reactions, and talking about one of our first relationships with chemical reactions, the changing of concentration and the rate of the reaction. In the next video, we're going to talk about integrated rate law. This is really important because with this rate law, we can find the amount of reactants at any given time throughout the reaction. So this point on these 2 video series on chemical kinetics is that we could take what we learn in general chemistry and take it to talking about enzymes, biological reactions, why enzymes are such good catalysts, and just on the grand scheme of biochemistry. But I also want to take this time to give out some thank yous to people that have helped me being able to continue doing what I do and create these infographics for you guys. First of all, I want to say thank you to the company Righty. Righty is an awesome company that provides really cool whiteboards that can re-stick on multiple surfaces like your desk and even the wall. So you can see in this on the side of my iPad, that black pad with the writing, that's where I've been planning some of my chemical kinetics notes for this video and future content. And I just want to say thank you. They provide these awesome products. I also want to give thanks to an artist on Instagram called Panderpaws. I'll link her and the company down in the description. She made these awesome, cute little Kirby stickers that honestly just made my day. So I hope you guys have a wonderful day. And yeah, thank you so much.